Dzień dobry. Chciałem was powitać w języku polskim, bo nie znacie tego języka. There was a few sentences in Polish language. I heard your language, but you never had Polish probably, so you learned something, right? Ladies and gentlemen, today I will talk about slow Swift. There's no assumption. Maybe it's fast, who knows? My name is Marcin Krzyżanowski. I work at PSPDFKit, where we build a PDF framework for iOS, Android, and web. Also, we have a PDF viewer application. It's a free application. You can download it from the App Store and check out our framework. You can find me on Twitter. Very easy handle. I have a website when you can find pronunciation of my last name. and I have a GitHub account. On GitHub, I mentioned three open source projects: CryptoSwift, which is the Swift implementation of cryptography, like algorithms; ObjectivePGP, that is implementation of OpenPGP, pretty good privacy; and Natalie, this Swift source code generator for storyboards. And I want to point to CryptoSwift here because this talk is based on my experience while working on CryptoSwift. So in 2014, Apple got us by surprise and present Swift, right? This is one of the slides they presented where they say, oh, well, this is beast. This is very fast language. So what they saw us, this is Python. Python is a base here. And there is Objective-C. At least we use that language. And there's a Swift. So turned out Swift in this example is almost 4 times faster than Python, and nobody used that. But it's just 1.4 times faster than Objective-C, which is not that great value. Why did we get Swift at all? Well, Apple had a need to give us a better tool. And they asked themselves, do they can improve Objective-C? And they answer, no. So they create a new language. Fun fact, I don't know how many of you knows that Arc, as we know it, is because of Swift. So by the time 2010, when the Arc was introduced, Chris Lattner already started working on Swift. And they added Arc to Objective-C, but they already thought about Swift. And this is why Arc is such a part of Swift. And of course, the C program is like a fast dance on a newly worked dance floor by people carrying razors. I don't know who said that. I tried to Google this guy, but it's fake. I don't know. So the Swift was invented as a secure, safe language, at least safer than Objective-C based on C would ever be. So we have a Swift, and how can we use Swift? We can use it as a script language, right? Like this. Just type Swift, and we have a prompt. We can type something and get a result, or below, we can add the header and put the Swift source code below and just run it like a Python and Ruby, maybe. But the problem with that is it's not optimized. This is just like debug build, if we would build. So it's slow. From my experience, and the project Natalie I mentioned in the start, I started as a script command line tool. Then eventually I switched to build time because the script version was very, very slow. So it's like 500 times to 1,000 times slower than the default optimized build. And this is true. This is also true if you debug the Swift, debug the debug build, right? It's very slow, and you should never look at the performance there. Otherwise, yeah, on the other hand, we have a compiled Swift, and this is what we work with. So what the benefits is of course, it's optimized, right? But the build times are quite significant. Let's consider this example. And I checked that yesterday because this is the old issue. There was another one, but the other one is fixed. But that one is not. Because this simple adding 6 arrays of integers is too complex to be solved on this machine, and this is the i7 Intel with 16 gigabyte of RAM and everything, right? Well, it's too complex. So this is the comma. And this is another example. Just recently, for CryptoSwift, I had this issue that something is compiling way too long. And I start to debug and find what was the function. And look, it took about 60 seconds to compile one function. And with this change, seriously, this is the only change, it took below 1 second. And why? Because I replaced the addition, right? So I removed the addition by calling the function advanced by, and what most important, I removed the bit shifting part, which is for some reason, and I know the reasons, is very complex to compiler to get reason about. One of the reasons is what Jesse said, this whole protocol-based integers. This is basically a reason why the integers are so slow to compile. And this, have you ever seen this dialogue today or yesterday, maybe? No? No? Okay, so I tell you. So there's a source code, you know. Let's go to abstract source tree, and there goes to seal. Seal is Swift intermediate language. And I mentioned that because Swift intermediate language is where most of the optimization of the Swift abstraction is going on. And this is the part that was added to LLVM toolchain for the Swift specifically. And everything on the right is just LLVM. So there's modules that are used for any other language that work with LLVM. So this is the building. So what can we do during the compilation? This is from the perspective of Xcode, but all of these options have the command line alternative. Optimization level, which is the most basic setup. Minus none is a debug. I don't have debug in my setup, but normally this is a debug setup. Slow and everything. Minus O is a single file optimization. This is the default release configuration for Swift Package Manager. And third option, minus O, whole module optimization. I'm sure you're aware what a whole module optimization is. There's a blog post on Swift.org about what is it, how it works. So basically, it takes all the files from the module and apply the optimization phases on all files together. So it have a wider perspective to apply the optimization. The next option is Swift disable safety checks. Swift is safe language by design, but we can disable that, at least at some parts. So to gain some speed, we can disable runtime safety checks. There's a checks like if the integer overflow or array index is, in some cases, overflow. Now, if we disable that, there's less code to execute, it's faster. Rather don't do that for debug, I'd say. Well, in tests, I do, but I have a reason. But for release, if you're sure, well, you can. This is the new one in Swift 4, Swift Enforced Exclusive Access, and quite interesting one. On evolution list, it has number 176, and this is the first part of implementation of ownership model in Swift. What it does, well, it checks the memory access, right? And it has three levels. Full, that is during the compilation, analysis during the compilation and in the runtime, or just compile time and none, so you can disable it. I use compile time because, well, it's good to check that, but it has impact on the performance in the runtime, so I disable that. And that one is the old one, and maybe it's not that obvious that when we generate debugging symbols, it has an impact on optimization. Why? Debugging symbols relate to your code. So let's say, for example, if the variable can be optimized out, normally it could be optimized out. But if you have debug symbols, it cannot be, because debug symbol relate to this variable, right? So it stays. So basically, some of the optimization cannot be applied if we generate debug symbols. It's very hard to, of course, debug binary without the symbols, but yeah, something for something. What can we do on the source side of the optimization? So basic one, and this is what I use. Instead of adding, subtracting, or multiplication, we have this version with this sign. I don't know the English. What is the English? Ampersand, yeah. And this is the version of the operation, but without checking overflow, for overflow. It's faster. It's not that faster that you will see normally. But if you do like 1,000 of iteration with the calculation, you will see a few, like 5%, maybe more percent increase in the performance. All that checks costs. The another one, this with the init, is for int. And whenever you want to cast one integer to another, like integer 32 to integer 64, there's a initializer, but there's also this truncating if needed initializer that all it does, it just copy bits from one to another. There's a fast path that just copy without any checking, and you don't care, right? This is very fast, and I use it a lot. Another thing is in-out parameter. This, I don't know for how long that will stay, especially with this ownership model changes. But for now, in-out parameter has a value that is passed in to the function, is modified in the function, and is passed back out of the function to replace the original value, right? If you think about it, it's like there's a copy, right? At least there's assigned to the temporary variable, and then back to the variable that was passed to the function. But because of the optimization, it can be optimized to the pass-by value that works basically like a C, like in C. You pass, you work on that sum variable, and that's all. There's no copy inside. I quote Chris Eidhoff here. I find it like right. He said, during the break, I refactored the parser combinatorial library to use in-out instead of returning, and it's 5 times as fast. And it's really that fast. Like, because we don't have a copy there, and copy is very expensive. And pointers, it works kind of like a pointers, are very useful for the performance. If you look at the Swift standard library, in-out is used everywhere. I was hesitating to use that, but then I thought, well, everyone used that, why shouldn't I? No. So I used that, and it's very fast. Source optimization, some obvious. You know that probably. Struct over class. Everyone says that. Why? Because struct probably will be allocated on stack, and stack allocation is fast. I will talk about it more. And class can be allocated on stack, but most likely will be allocated on heap. And class has more things, like there's inheritance that has to be checked in runtime. So there's more jumps when you access the class than the struct, probably. Final class is kind of solution because there's no inheritance, so like an object is more complete, so it's easier to get the shortcuts. And the private final class is even more strict. More strict. Now I don't know, you're smart guys. You tell me, look at this code. There's a 4 million count, and I allocate the array, 4 million with 7s. Then I iterate over the array, right, and increase count. There's one line, and it executes on this machine 2.7 seconds. There's one line, exactly 5 characters, change, that will make it twice as fast. Does anyone have any idea what can be done here? Close, not uint. It has to be int. So if you didn't notice, it's just that, right? And the speed up is like this. It's old. I think this is the old issue. Something, somewhere, do not optimize other types than integer. Who knows why? But it's very visible in the look. The other one is my personal advice. If you want to write more performance Swift pieces, just don't use Swift map, reduce, and so forth. So for loop over. And I have an example. Very, very easy example. There's a reduced version of it multiply the value of dictionary by 5, basically. So it's reduce and return dictionary from with update. And it's written Swifty, very Swifty, right? There's a reduce, there's extension, everything is Swifty. Of course, we can do the same just with the for loop, and it's just faster. Look, maybe it's not much, but look, this dictionary has only 2 keys. If it has like 1,000 keys, I'm sure difference will be more visible. Okay, next, inlining. You know what the inlining is? Just a nod? Okay, Nick knows, come on. No, okay, so inlining is if you have a function and if you call that function, instead of jump to the function, execute, and back to your code, you can just take the body of that function and inline in your code. So there's no additional jump to the function, right? Benefit is this jump. It always costs. So the code looks like it would be body just included in your body. And it happens automatically. SIL does that, LLVM does that. You check the boundaries and decide whether the function can be inlined. But we can help with that. Using this private attribute, we can give a hint to the compiler to inline always. And it's just a hint, because this is the actual force to inline function, transparent. If you look, again, if you look at the standard library, both are used everywhere. With a public interface, so if we have a public function, we can use inline attribute, and this is basically a hint. So it can be, if you use from the outside, the compiler can decide to inline. Yeah, but it, of course, like everything, it has pros and cons. The con is the binary is bigger, because code is copied everywhere where it is inlined. And we don't have that problem yet, but if we had an ABI, your source code had to be recompiled whenever the library you link with changed the method that was inlined in your binary, right? Because there's no jump to the library. It's modified the code, so it has to be rebuilt. Yeah. Oh, good time. So now we have memory. You know, with a memory, we can deal with in Swift in various ways. I choose playing with an array of bytes, but you can use data. I choose an array because that was the time before the foundation was available on Linux, so that was the design decision. But the same applied to the data. Array and data, they both use copy and write. The copy and write was presented by Omer yesterday, so you remember, just like this diagram. Yeah, so I have a 1,000 bytes, and I modify the fifth element, right? So that's the normal way. But what if I got a raw chunk of memory, and I get no copy and write, no arc, so no retain, no release, but I just have to allocate and deallocate buffer by myself. So we go to the C level. That would be like this in Swift. I allocate, it's complementary, like it's the same. Up is array, below is a collection of bytes. Allocate the bytes, initialize, modify fifth element, deinitialize, deallocate, and recreate the array out of the buffer. What is the gain? If I have a loop, inside where I would change a lot of values of that buffer, with the array, they will be copied at some point, right? Because I modify the type. So that would copy, change one copy. With the buffer, well, it's up to me. So I can change whatever I want. The buffer is a collection, so I have a convenient access to the bytes. And after I finish, there's one copy probably. I'm not even sure if the last line would be a copy or just, or if that just get the buffer. Yeah, it's wrong. The allocation should be after the array. The thing is, there will be at most one copy, right, of the array. If the array is small, yeah, maybe that's not a problem. But if the array is quite big and you have 1,000 of iterations, a copy of 1 megabyte, yeah, you will see that. And look, turns out just initializing the array is about 10% slower compared to allocate the chunk of memory. It's not that surprising, but yeah, still, if you care about. Now, look, do you remember that from your class? Like typical, let's say, memory layout. I deleted a lot of slides with that, but I left that one. So yeah, we have instructions from the bottom. Instructions, literal static data. There's a memory that is allocated during the compilation, right? Then we have a heap space, dynamic data, some free space, and stack. Stacks goes from top to bottom, heap from bottom to top. At the bottom there's 0 address, at the top is maximum. Stack allocation that can, we know, I already said that struct can be allocated in stack, is very fast. Why is fast? Because, somebody told us yesterday, because it's just a change of value of one special register. You change the integer and it points to the other place and you get that chunk of memory, that's all. With a heap, it's different. It's not slow, but it's slower, definitely from stack allocation. You allocate page map. You don't need all maps, so yeah, you don't need all maps. You get some fragments, so there's a fragment table. It's slower. There's more operations to perform to allocate the same amount on the heap. But what can we do to improve that? We can, for example, pre-allocate some memory. With the array, normally array has a mechanism that increase the internal buffer, right? It's not that if you add 1, it's always reallocate +1. It will allocate some more. But if you know upfront how big the buffer would be, you can just reserve the capacity, which is allocate that amount of memory once, and you can work on that. So you avoid some reallocations. And no quiz. A quiz is fast. And this simple example, array, 1 byte, and I append -1, append 1. How do you think where the array will be allocated? I can wait. I still have 2 minutes. Okay, who knows? Yeah. Well, yeah. Of course, yeah, it can be static data too. It's stack. If you're not sure, you can stop the debugger and check the RSP. So the value of register is quite high, right? And then check the variable in the frame, stack frame, and see, oh, it's quite similar, so it's probably on stack. The heap would be low value. Yeah, so it's on stack. The same example, but one of the integers is appended asynchronously in queue. Yeah, it's a heap. You know why? Because the compiler knows that it will escape. So it will not survive in the stack frame of that function. So it has to be allocated on the heap. And in here, this value, very low, that means it's a heap, basically. And the last one, it's a struct that is allocated in a function, and something is happening asynchronously on the queue. It's not class, it's a struct. What will happen? Heap. It's heap. So whoever say you that struct will be allocated on the stack, it's not true. Struct will be allocated whenever it has to be allocated. So if it's called from the closure, it will be definitely on stack. If it's like this, escaping, on heap. If it's escaping, it's on heap, right? That's over. That's close of the quiz. But we go to the generics. I love it, and I deleted a lot of slides yesterday, but I had to. What is generic code? Generic code enables you to write flexible, reusable functions and types that can work with any type. Yeah, and you can, of course, add the constraints. This is real-life generic constraints I got for once. I showed it just to show you that generic can be quite complicated, not just for us, but also for the compiler. And look at this code. That's not my code. That's the code you can find in the Swift repository. But it's a class, generic class, that conform to some protocols, doesn't matter, and has a function play. That function called ping, right? And this, in runtime, takes 20 milliseconds. Yeah, 20 milliseconds. 20 milliseconds to execute on my machine. Now look what I did. I specialized this function, effectively the whole class, and it ran 0.06. So look at the difference, right? Just by adding this private specialized attribute. Why that happens? Before I go to the next slide, is very hardcore. So generics, when you create them, are not specialized. Compiler look at all the use of generic function or class and look with what type it is used. Gather all the types and specialize for that types. So that's fine. Inside the module, compiler will do that specialization automatically because you can see what types were used. But if that be your public interface, it won't, because generics can be only automatically specialized inside the module. Your other module, your application, let's say this is the library framework, your application would just see game t-pingable, and it won't be specialized. That's how it works. The only library that can do that magic is Swift standard library. That's how it looks. This is a SIL, Swift intermediate language. The version you can see now is unspecialized version of game class. After I add specialization, it added one block. It moved that block, that BBB0 that was unspecialized, to BBB1, and added this block BBB0. What's in BBB0? BBB0 decide, there's a condition, decide if I get the int jump to BB6, that is a specialized version of this class, and just ignore the unspecialized. Problem with unspecialized is that it's slow. Everything is resolved in runtime and is very slow. Specialized already assume, okay, the input is int, so I can optimize the code, blah, blah, and execute in that fast. So generics, in generics, the optimization is automatic whenever it is possible, so it is in the same module. Otherwise, you can use this private attribute and just say compiler to optimize the function. Whole module optimization won't help because it still works on the same module. Yeah. Sometimes it won't, so you have to help with the specialize. And I have a lot of commits where I degenerics my code. I avoid the generics in the public API because of that penalty. let's recap. Debug is slow. It's just very, very slow. You should not do any performance tests with the debug build. You can pre-allocate memory to avoid reallocation. Stack is fast, heap is cheap. Copy is bad. Any kind of copy memory is slow. And yeah, generics, that's fun, but use it carefully. And my favorite, less Swift is faster Swift. Okay, thank you very much.
Thank you, Marcin, on your personal views about Swift. Any questions from the floor for him?
Hi. What's your opinion on Swift being used to write backend? Example, Vapor.
Sorry, I didn't hear.
What's your opinion on Swift being used to write backend? One of the example libraries, Vapor.
On backend?
Yeah.
I didn't use it on backend. Well, it's good. Like Swift on Linux is getting better and better. Of course, the foundation is different. It doesn't work. Somebody said that. It's different version of foundation, but you know, it's a good language. It can be fast if you really think. And on Linux, it's not that problem because mostly everything is wrapped from the C library anyway. So it's just abstraction layer. Not many libraries are pure Swift. So I don't have strong opinion on that. I hope it will be big, so it will save our, work, jobs, when the mobile era will end up. So I hope it will be big.
Okay, thank you. Do you have any more questions? We can take one question.
Hey, for the example of array allocated in a stack, because so it should be decided at the compile time, right? So I don't understand how compiler knows that, for example, at one time we have enough memory for stack, because stack memory is limited.
Yeah.
Sometimes you have a big array and it cannot be fit in stack, right?
Yeah. So if you allocate on the stack, probably I don't know if they have a limit. Like, what is the limit on Linux? I don't remember. You can change it with a ulimit, right? Option. How?
But they don't put arbitrarily low.
I think there is a value, arbitrary value for the max stack.
Like 3 words.
Yeah, maybe 3 words. So you will get just Stack Overflow, right? So I didn't check that. I think there's they check if it's too big, they will allocate on heap. But I'm not sure. The small one you can allocate, like I allocate mostly like 64 bytes, so that's not that big. If you allocate more, I'm not sure. I would say it will decide, the compiler would decide to allocate if he knows the value up front, because he may not. It may be just variable, right, passed from outside. In that case, heap cannot reach the stack, so you get a Stack Overflow in the runtime.
Okay, thank you.
Thank you, Marcin. I guess for Swift it's really complicated, but if you're really interested, you can deep dive into the code to see what's really going on underneath. Okay,
Thank you
let's
very
give
much.
another applause.